Welcome to the case study for best practices for PROTACs. Here we will look at SMARCA PROTACs and see how some of the practices discussed in the webinar are used to validate chemical probes for SMARCA proficient cancers. Let's start with the target, SMARCA. BAF complexes are known to regulate chromatin and transcription, and mutations to this complex can be found in approximately 20% of human cancers. These cells contain one of two mutually exclusive, yet with almost complete sequence conservation, ATPases, SMARCA2 or SMARCA4. Further to this, genetic screens using RNAi show dependence of the activity of one of these ATPases when the other is mutated or missing. Previous work in the field includes suppressing SMARCA2 activity, and while dual allosteric inhibitors were able to show antiproliferative effects in SMARCA4 mutant xenograft model, other work showed that ligands targeting the bromodomains of SMARCA2 and 4 have so far been unable to exhibit the desired antiproliferative effects. In the PROTAC case, our therapeutic concept is to induce synthetic lethality by removing the present SMARCA ATPase in a SMARCA deficient cancer, resulting in the selective cancer cell death. Cells require the function of at least one SMARCA gene, and so can tolerate the inactivation or removal of one of these when both are present. When only one exists, though, for example in a cancer cell, this can lead to the cell's death. In PROTAC programs, often known small molecule ligands are attractive starting points, provided a suitable conjugating exit vector can link to a suitable E3 ligase. With this in mind, we utilized our own experience with VHL ligase binders alongside known Genentech SMARCA bromodomain binders to create our first library of PROTACs. With 10 linkers giving 10 PROTACs, we assessed these somewhat crudely but quickly, only at a single concentration and single time point. All of these on the surface appeared to be what we would class as non-degraders, with Dmax values below 50%. However, because we only used single point testing, it wasn't quite as straightforward as this, as testing multiple time points or concentrations, especially early in a project, can afford your first lead towards project directions. To tell the full story here, I'd like to bring your attention back to what was discussed in the webinar and focus on the formation of ternary complexes. As we discussed in the webinar, ternary complexes are essential for inducing degradation of the target protein, and complexes that form at higher affinities tend to be more potent and faster degraders. Cooperativity, or alpha, is one way that we measure if the ternary structure is favored, where the second association is aided following the initial association. The free energy change, or the delta G of the complex formation, can also be used to determine the stability of the overall ternary complex. Stable, positively cooperative ternary complexes greatly aid with crystallographic studies, which are crucial for the structure-guided optimization. Rather than just relying on our single-shot testing, we further analyzed the biophysics of these 10 PROTACs. Pleasingly, PROTAC 1 through proximity assays showed that a ternary complex was forming. We further tested PROTAC 1 at a range of time points and concentrations to show the first signs of SMARCA degradation. This convinced us that further optimization could be possible. Additionally, we were able to gain a crystal structure, allowing for a rational design through a structure-guided optimization approach. With the ternary crystal structure of PROTAC 1 in hand, we assessed the ternary interface and determined we were able to target specific residues. In this case, tyrosine 98 of VHL was targeted, along with simultaneously rigidifying and reducing the polarity of the linker. With the introduction of a phenol into the linker, a further ternary crystal structure was gained, and showed a near identical ternary complex forming, with the desired tyrosine interaction. Here we also noted there was some potential strain in the linker between the VHL exit vector and the phenyl in the linker. We decided that we could introduce some modifications to aim to release this strain. With the aid of multiple ternary crystal structures, we were able to design ACBI1 in an unprecedentedly low number of iterations from our initial hit, PROTAC1. As we see in the table, PROTAC1 exhibits moderate binary affinity towards the protein of interest, but positive cooperativity, or alpha, helps this have excellent ternary affinity, as shown in the plus BCB column. The compound also shows modest ternary stability, as shown by the delta G and half-life of the ternary complex. As we introduce the phenyl into the linker in PROTAC2, we see a jump in binary affinity towards SMARCA to sub-micromolar IC50. Remember that this was a modification to target the ligase protein, not the protein of interest side, so it was a pleasant surprise for this compound. As we hoped, it boosted affinity to BCB and afforded a cooperative compound which greatly aided ternary affinity alongside a more stable complex. This all contributes to cellular degradation data of over 90% degradation with a DC50 of 80 nanomolar. Finally, moving to ACBI1, we barely change the affinity towards the protein of interest, but an excellent cooperativity value gives rise to a low double-digit nanomolar ternary IC50, as well as a super-stable ternary complex. As you see with the cellular data of ACBI1, this becomes an incredibly potent degrader with single-digit DC50 and over 90% Dmax. Whole cell, unbiased proteomics also shows the selectivity for ACBI1 towards SMARCA2, SMARCA4, and PBRM1 when analyzing the relative abundance of the protein levels versus a DMSO control. The use of cis-ACBI1 allows us to critically investigate the effect when E3 ligase binding is abrogated. Flipping the stereochemistry at the highlighted position on the E3 binder renders binding to the E3 ligase negligible, and so the compound is acting as an inhibitor, rather than through a PROTAC mechanism of action. This allows us to investigate any potential off-target or downstream effects. Western blot plots also show this, where the lead compound reduces levels of SMARCA2, SMARCA4, and PBRM1, while these are left untouched in the cell when treated with the negative control, or just the SMARCA ligand. Apoptosis measurements following treatment with ACBI1 show a similar effect on caspase activity in SK-MEL5 cells to doxorubicin, a chemotherapeutic drug. Additionally, the lack of caspase activity in the cis-ACBI1, which is identical to the DMSO control, confirms that the vulnerability of cancer cells to SMARCA subunit loss can be recapitulated through chemically induced degradation. Right from the outset, we knew we were driving for an orally efficacious compound, and as such, with excessive hydrogen bond donors, the SMARCA binder was known to be suboptimal. So we took inspiration from literature and in-house studies to optimize with a more suitable PK profile in mind. Compound 1 was designed by colleagues at BI and found to have appreciable binary affinity towards the SMARCA bromodomains by SPR. We also noted that it binds in the same SMARCA protein pocket, with similar interactions, as we expected. A modification of the SMARCA binder with a linker of the similar length instantly saw the generation of a selectivity window between SMARCA2 and SMARCA4, albeit as a partial degrader. A new ternary crystal structure also informed us of further possible modifications, namely changing the exit vector from the VHL binder from a phenolic to a benzylic position. Here we see the return of single-digit nanomolar DC50s and near full Dmaxes to the detriment of selectivity. BI-0883 was highly effluxed and also not orally bioavailable. However, it did show tumor growth inhibition when dosed subcutaneously, along with the complete removal of SMARCA levels at the end of the study. A move to longer all-carbon linkers improved SMARCA cellular degradation and reopened the selectivity window of SMARCA2 versus SMARCA4. While the compound was still moderately effluxed, this change also brought in the first signs of oral bioavailability. Identical SMARCA2 depletion levels were noted at the end of the study with mice xenograft bearing tumor cells, though this time dosed orally. And combining all of our learnings, including a chiral or a magic methyl into the linker, both increased the selectivity window and impart significant oral bioavailability. The magic methyl is a well-known trick in drug discovery to improve PK or PD properties, and in this case we found that it encouraged the PROTAC to adopt a hairpin-like structure, which clearly benefits the overall profile of ACBI2. As always in our programs, we check for selectivity and off-target effects by proteomic analysis. Here, ACBI2 shows a similar selectivity towards SMARCA2 and PBRM1. PROTAC mechanism of action is also confirmed through the use of E3 ligase, proteasome, and nedylation inhibitors. Here we can see that when cells are treated with the PROTAC, we remove the SMARCA and PBRM1 proteins, though when co-dosed with the respective inhibitors, the PROTAC mechanism of action cannot proceed, and so these proteins are left untouched. ACBI2 also behaves in a dose-dependent manner when orally dosed, meaning larger amounts of SMARCA remain when lower treatment doses are used and scales appropriately for higher doses, up to near complete removal at 100 mg per kilogram. It also shows moderate tumor growth inhibition in multiple SMARCA4 deficient cancer models. This effect is not limited to immortalized cancer cell lines either, and human whole blood assays have shown that we can recapitulate the complete selective SMARCA2 degradation ex vivo. This case study highlighted that using the techniques described, PROTACs can be generated to address the questions being asked quickly and efficiently, leading to oral and efficacious lead compounds. Rationally designing these with the use of ternary crystal structures allows speed in the fast-paced pharma game, and that these compounds can be more selective than their binder counterparts, even with such huge conservation within paralogs. In this case study, near-complete degradation of SMARCA2 leads to tumor growth inhibition in many mouse xenograft models. The study presented here was a collaborative effort between labs in Dundee and Boehringer-Ingelheim, and would not be possible without the work of each of the members mentioned here. Thank you for listening, and I hope this gives you an insight into the practices that we determine to be the best for driving our projects forward at speed.